talk of the day, Bakker and Tsimerman, talking about period functions and derivatives of period maps.
Great, thanks very much. Yeah, everything I'm talking about is going to be joint work with Ben Bakker and Jonathan Pila. And the basic question I want to get to fairly soon, and it's basically we have periods, we have period maps, which are sort of built out of periods. How can we recover the former from the latter? It's the sort of gist of this talk. But let me start very concretely. We'll start with a variety x over c, which I'll just keep things simple for now, make it smooth and projective. And how do we think about periods? The way I want to think about them in this talk is we can look at the Durand cohomology of x. And this is isomorphic via the isomorphism to the Durand isomorphism, sorry, the usual Betti cohomology. Okay. With complex number coefficients. And this isomorphism somehow encodes the data of periods that arise for x. So in particular, this here has a certain filtration, the Durand cohomology, where the lowest piece is just closed, different global algebraic differential forms on x, and the graded pieces, we'll look at the mth graded piece, and just get these hn minus m of x, omega x, and m forms. So how do we deal with periods? Well, let's let E with a hat on it be a basis for the Betti cohomology. And alpha with a hat. I couldn't think of a better letter than alpha, so it's alpha.
Then closed.
Sorry?
Then closed automatic.
Yes. I'm having a brain fart, sorry.
The previous
Bottom line.
Where are we looking?
The global forms are closed.
Oh, global form are closed, yes. Sorry, that's right. Close automatic, you're right. Auto closed. And this is a basis for Durand cohomology. H and Durand X. And then I'm going to write here because this is a bit low, I think. So what we're going to do is we're going to define the periods as the coefficients.
Well, E over Z or Q or something?
Not at the moment, but in a minute I will. Yeah. Coefficients of the change of basis vector matrix from alpha hat translated to E hat. So of course, as you point out, at the moment this could be any complex number. It's not very interesting. It could just be all ones and zeros, for example. So some remarks about what's happening here. So if alpha 1, say, or alpha I, is actually in this bottom filtration piece, so it's represented by some differential form omega, then Mij is just the integral along the cycle Ej of alpha I. So these are sort of what we classically think of as periods, at least in a smooth projective case. Okay, now, of course, if we also take E hat to be a Z basis, and we assume that X is defined over, say, Q, for example, and our alpha hat is the basis for the Durand cohomology over the Q, then we get sort of, then we get sort of classical number theoretic periods. things like volume data and stuff. And here we have the Kontasevich-Zage conjecture, the Grothendieck period conjecture. So it's Kontasevich-Zage. So the Grothendieck period conjecture. You can add sort of Andre's name, who refined the Grothendieck period conjecture to include Chenio's conjecture, and you get a whole bunch of interesting statements about these periods, none of which I will discuss here. But that's sort of the basis for how I want to think about periods. What I want to do is I want to move to the functional setting. Is this a... Okay, I'm going to learn from Philip's mistakes. I'm sure my blackboards all go up. So I want to think of really period functions, so something like log being the prototypical example. So the version here we're going to look at is we're going to look at a map, F from X to S. And again, this will all be erased later, but let's just think of a smooth projective map just to keep life a little bit simpler. And so now what we can do is we can look at Hn deriv of X over S. It's just a derived push forward of the deriv complex, the relative deriv complex of X over S. And what kind of object is this? This is a vector bundle, but it's got a connection on it as well, so it's a flat vector bundle on S. And then we also have just the push forward in the analytic topology of C here, not Z. So now the Z is really not going to play a role in what I'm going to say because it's the functional setting. Integers no longer exist. And so this is a local system. On the analytic topology of X. And once again, we have this isomorphism. If we tensor up from our local system to a vector bundle.
You have the tensor on the other side too.
Yes, you have to, sorry, completed over here as well, 100%. And same as before, this comes equipped with a filtration, the bottom piece of which is sort of actual relative differential forms that you can actually integrate. So we'll call the periods of F to be the coefficients generated by the coefficients of a change of basis matrix, where this is a basis for Hn deriv. You can do it in Shifa language, but I just want to keep the sort of period formalism that I'm used to with like actually integrating. This is a basis locally for Rn for this local system, F star C. And how do we actually make sense of this? Because periods have monodromies, they aren't like global functions. So you can do a variety of things. You can pass to universal cover or whatever it is. What we're going to do is we're going to fix a little s in big S, and we're just going to take stocks everywhere at little x. We're going to complete at this little s. And what is this guy here? I said it's generated by these as well. So what we get is a well-defined module over the local ring here. S at our chosen point little s, which is of course fully sort of artificial. You could do this at any point little s that you want to do. Okay, so that paper has the word quasi in it, and I think the abstract has quasi in it as well. So let me say like a word about quasi periods. What is this quasi? I don't think the word quasi is one that I knew. Quasi, exclamation mark, periods, is one that I knew in this context until Jonathan explained it to me. But I think it's common in some, for some people who think about periods from certain perspectives. And the point is, you don't really want to integrate arbitrary Dirac classes. You want to integrate differential forms because we know and love differential forms. And so, as an example, we take E to be an elliptic curve and take U to be E minus a point. So U is now an affine curve because I punctured it once. Then we can take the Dirac cohomology of E, put it inside the Dirac cohomology of U, which is E minus a point. And now here, this is generated by omega, where omega is the actual form on E, the global invariant form on E. And then we have another form, omega prime, where this has a double pole. And so what we can do now is instead of integrating random classes, we can take this meromorphic form, we can integrate that along our periods, along our cycles, and that gives us our sort of missing two periods that you can't see if you want to integrate forms from before. So this all makes sense in a similar way, which we talk about in our paper. It's also classical. If you have like projective things, you can sort of puncture them and then get everything using actual forms. So all these periods, even though they look a little bit more exotic at first, they really all can be thought of as integrals of forms along cycles. Any questions so far? Okay. So this is all set up. So now the other half is period maps. So now given setup from before, on this HN Dirac, actually carries a variation of Hodge structure. That's a bit of a lie. You have to put the word prim here. You have to deal with primitive cohomology, but that's okay. You can take the word prim and put it everywhere else in the talk as well. So we're just going to pretend that all happened.
Well, you didn't put polarized in the to say you can erase that.
I'm sorry?
You didn't put polarized in the VHS.
You're right, but I should have.
So
Then I
you
would
could
have
erase it.
I'm sorry?
Or you could erase it.
No, but I'm going to keep it. But thank you for giving the option. You're right. I do want polarized. Because I want a good period map. So what this gives me, is a corresponding period map from S to D mod gamma, where D is sort of some Grossmanian variety or some open in a Grossmanian variety. Exactly keeping track of the filtrations that we talked about before, and gamma is some arithmetic. Records the monoderivative of our local system. So I could give more notation and give more detail, but I don't really want to, so I won't, because we're not going to talk about this with that much precision. The point of this is, given this data, we can ask what sort of functions can we build just by looking at the Hodge variation. Right? So given, let me move so I have some space again. Yeah.
You have done so far, you haven't used the filtration. In defining
Say that again, please.
the periods, you haven't had to use the filtration yet. Like
For the periods themselves, no. That's right.
This is the first place where you're using.
This is, yeah, so to get the periods during the filtration, and we're only going to use it to build the period map or the variation. That's right. So given a rational function, let's say psi on V check, like convectification of V, what we can do is we can look at its pullback, so phi pullback C at S, and we get something here, assuming a rational function makes sense at S. And so this will give us some kind of coordinates sort of on our Grassmannian, which is ultimately built out of periods. So it's not hard to see that this will lie as an element of C drawing the periods coming from it. So it's just sort of built out of certain Plucker coordinates here. Okay? And so now what we can do is we can define C of phi to be the field generated by all these functions. So now for elliptic curve, which we'll do in more detail in just a minute, it's just like the tau coordinates we have by living in the upper half plane. And the question that I want to ask, which I'll talk about the inspiration a bit in a minute, is can you recover the periods, span the field, whatever?
By this thing, don't we need some kind of something kind of modular about this family or something of that sort? This is just any old rational function.
Here? This is a new rational function, yeah.
Oh, it's an element of. You're not saying you get all of them.
No. Yeah, of course you can. Yeah. So can you recover this from the set of all of them? Okay. So somehow the sort of meta motivation for this is it's always bothered me that we have this interesting space D mod gamma with rich arithmetic, but it only looks at this like small part of the periods. So can you put the periods back in some way, without the G of R mod G of Z, without the mod M or whatever? And the answer is I don't know how to do that yet, or if that makes sense still, but this is at least some kind of well-defined question, semi-well-defined question that you could study. So that was the reason for formulating this. And the answer is, of course, this could be much smaller than this because you're losing a lot of information. That's not clear. That is clear. But the observation we got started is that if you look at the field generated by the periods, which by the way I've defined that, by the way, contains all the rational functions on S, because I can pick whatever periods I want. If I look at this field, this isn't just an arbitrary subfield of the completion or whatever. This is actually closed under S derivations. Right? Because if I take a basis like this, and if I apply some derivation to sort of the EI coordinate of some alpha j, then this is just applying EI star to D applied to alpha j, which I can do because I have a connection on my vector bundle. Just like if you differentiate periods with respect to the base, you get other periods, things built out of other periods. Okay, so with this observation in hand, this motivates the following definition, which is let C delta of phi be the field generated by C phi and all S derivations. Okay. So we take the smallest sort of differential field, this sense which contains all the coordinates coming from the variation of Hodge structures in this way. Are you capturing everything? So our theorem is the following, which I'll state in this context, and then later I'll explain how to move it to a slightly more general context, which I think is a little bit clarifying. First of all, I mean, I've been saying this implicitly, but I'll just write it down formally. If you look at this field, then it's contained in the period field. So that's not especially surprising, what we've been saying. It's back. And part two is that, so they're not quite equal, but their algebraic closures are equal. If and only if the local system contains no direct summand, which is unitary. So I do need my polarization. With infinite monodrome. Okay, and otherwise it's smaller, and you can pinpoint exactly how much smaller it is. It's smaller by exactly sort of what's missing. So why is this condition here? Well, it wasn't in our first draft, which was wrong, but then the proof revealed it needs to be here. And if you look at it, you can see why, because if you have this component, being unitary means the period map is constant. You're sort of losing all information. And then if you happen to have finite monodromy, then it doesn't matter because all your periods are algebraic anyways. But if you have infinite monodromy, then your periods have some transcendence to them, and so you're missing them. Okay? Any questions about the statement? So one remark I'll make is that this is heavily inspired by a paper of Bertrand and Zudlin from, I didn't check the year, 2002, I think, somewhere around there, who did this for, who established this for Siegel sort of modular functions. So they looked at AG, looked at the field of Siegel modular functions, and they started differentiating them with respect, to the coordinates on the Siegel upper half planes, just the coordinates of the matrix, of the matrices, the symmetric matrices. And they showed that you add, that you get what you should. And they had some of the same formulas that were used sort of established, so they understood quite a lot of the picture.
In some earlier work, I thought there was like a Schwartzian generalization of the Schwartzian that came into this functional transcendence.
Yeah, so this is in our paper with Bakker and Pila, when we did X-channel for Shimura varieties, we were studying jet spaces, which will come up, and we had some Schwartzian stuff going on. Yeah.
What's the context of get this point as you take what kind of neighborhood? Formal, analytic?
Yeah, so everything, we just need something big enough to contain everything. So you have formal neighborhood.
And you lift that to the map to D instead of D mod gamma.
Correct. Exactly. Mm-hmm. Yeah, so in fact, you don't even need, I mean, you can just pick local coordinates and map to D check directly. You don't, the gamma plays no role in what we're doing. Or in the statement. Other questions?
Isn't the local system semi-simple? Because it doesn't
Right,
have
so-
the VHS.
Yes.
Then how can you have what's an example of having a direct summand with infinite use?
Oh, even in the semi-simple case, you can have it. So for example, look at like a Shimura variety, where the group has some real compact factors. Right?
Sure.
Then over C,
yeah.
decompose.
Yeah.
So just because you're unitary doesn't mean your Galois conjugates are unitary.
Sure.
Which is actually a huge problem for a lot of like Simpson type stuff.
Sure.
Yeah, so in particular, this is equality holds for like Shimura varieties without complex factors. The Bertrand
Can you characterize these, like say, the transcendence degree to these things as, so I get my head around it, as like, you know, the dimension of the kernel of the image of something?
Yeah, 100%. Well, I'll say some more stuff when I take it to answer it, but it's some straightforward thing. Okay, before I move on to some more theory, let me do an example. So this is either going to be a terrible mistake or a brilliant move. So you guys can tell me which afterwards. But I want to do one example that's concrete because I think seeing an example is worth 1,000 theorems in this case. So the example I want to do is the example of the universal elliptic curve. And it's sort of, I mean, it's not that hard, but it's not trivial to find coordinates in which to do things where you can actually compute everything. So I'm going to try to do it quite carefully. We'll see if it works out. So the way we'll do it is we'll let S be the modular curve. And we'll think of Sn as the upper half plane mod gamma, where gamma is something in, well, but this is going to be some modular curve, mod SO to Z. You can take SO to Z, but you can take a gamma if you don't want to deal with stacky points, which I don't really want to deal with. This is really a big deal. And then what we'll do, we have the universal family, X to S, of elliptic curves. And I'll think of it in the following way. The analytification is going to be Z squared semi-direct gamma acting on C across the upper half plane. So this will give you the modular curve. And the C mod Z squared gives you the elliptic curve, and the semi-direct product and how they sort of intertwine. That works. Maybe see if that works. And the action, if you haven't seen it, is sort of the mn part of Z squared just acts on the Z by tau and 1, comma tau. And the SL2 part, of course, it acts on tau in the familiar way, and the way it acts on Z is you just divide Z by C tau plus D. Here you have A tau plus D. Okay, so some people have seen this before, and I'm sure some people have not, but this is the explicit action on C cross H. Okay, so now we're going to find some forms to integrate. And so the naive guess is dz, but dz doesn't work because I'm going to call this gamma. If I pull back dz, and of course I get dz over C tau plus D. Now you can fix it because you can compute that gamma star, or let me write it this way. If I look at J prime of gamma tau, I get C tau plus D squared times J prime of tau. So I want to divide by the square root of J prime of tau to make this actually a global one form. And so I need the J prime of tau square root to make sense. So what I do is I let omega be
Differentiation with respect to what? J, you have J prime.
with respect to tau. With respect to tau. The function of tau. Yeah, that of course. So I'm going to divide dz by J prime of tau to the 1/2. This is a multi-form. It gives some double cover. So I'm going to let y be a cover of S such that omega on y is well defined. And I'm going to base change everything to y and work over y. Okay, so now I can start integrating. The periods of my elliptic curve are just C mod 1 tau. So it's just 1 and tau. So, I get the two periods I get are integral of omega from 0 to 1 in the z coordinate, and integral of omega from 0 to tau in the z coordinate. And that gives me just sorry. No, I'm going to multiply, not divide. Right? Because here it's times, yeah. So this is dz times j prime of tau to the 1/2. Apologies. So I get the square root of j prime and tau times the square root of j prime. And that's sort of half the periods. Now I could compute the quasi period that involves some wire stress functions, which is the way we thought of it, and that seems complicated and bad. So we don't want to do that. But we don't have to do that because everything we have is closed under derivations. So for the other two, we just differentiate with respect to the coordinate on S, which is del by del j. And del by del j is not so bad. It's just del by del tau times j prime inverse. So the other two periods are, you can work them out, they're R1, which is 1/2 j double prime of tau divided by j prime of tau to the 1/2, and R2, which is tau times R1 minus j prime of tau to the minus 1/2. At least that's what's in my notes. So it's close enough to correct. We only care about the field anyway, so it doesn't super matter if we made a mistake here or there. So in particular, the period field that you get is, we're working over y, remember? So we get all the algebraic functions in y times tau, adjoin tau j prime of tau to the 1/2 and j double prime of tau. And you can actually check because j satisfies the Schwarzian equation for its triple derivative. If you keep differentiating, you won't get anything new. And the other one is actually much easier because the only rational function you have to adjoin from the upper half plane is tau from P1. This generates everything. And now all you got to do is apply all derivations. You got to differentiate with respect to j over and over again. And all that does is give you j prime of tau and j double prime of tau. Okay. So what you notice is that the algebraic closures are the same, but the fields are not the same. Because j prime of tau to the 1/2 is not going to be inside the adjoint y. J prime is transcendental. Okay, so you really need the algebraic closure already in this case. Okay, we can take a poll later for whether that was time well spent. So what I want to do now is,
You tried to do this example.
Yeah.
With the Legendre family.
yeah,
That pretty much.
I think it depends who's doing the computation. For me, this was much easier. For me, this was much easier because, well, I don't know. It just, I don't know. It's all like, yeah, we can talk later. I would not be surprised if you could do it with the Legendre family as well. But somehow here you can see things. I mean, yeah, I don't know. Okay, so
And if you don't know that j of tau satisfies the differential equation, can you recover it?
can you recover it from here? Ooh, good question. Yeah, you could. You could recover it, but you would have to. You could recover it by keeping track of the relative differentials that you have and applying your matrix, your derivation operator twice, and then expressing it as a combination of the first two. And the second derivative would give you a j triple prime. And in the end, you would get a relation between j triple prime and the lower derivatives. So that's what would happen if you did that. I think we might actually come close to doing that in our paper with Mott, actually. Actually, for sure. We do something similar to recover the Schwarzian equation, but we haven't worked that out. Other questions?
Do you know ahead of time what the degree of the integration? Instead of passing to the algebraic closure.
No, so actually that's something that we thought about, and yeah, that's an interesting question. Like how far away they are from actually being equal, being algebraic? No, I think, yeah, maybe the proof, well, I'll say something about the proof and maybe you can see where to do it, but we thought about it, I think it wasn't obvious at least, right? I mean,
The principles in the proof, but it's not.
maybe it's in principle there, but maybe it's not clear. It's another, anyways, yeah, not a language that was super understandable. Yeah. To me at least. Okay, I want to explain how to generalize this a little bit. Because, for example, we talked about smooth projective, and smooth projective has nothing to do with anything. You can replace the family with an arbitrary family that's topologically constant. So you can talk about periods, but in fact, you can go much more general than that. So what you can do is you can let this be a flat bundle over S. And now sometimes write V just and remove the connection just because I'm lazy, but you need the connection for almost everything. And let L be the local system. The Riemann-Hilbert correspondence in sort of the easy direction, which is just look at the flat sections, you get some local system. End of story. And so then you have an isomorphism, analytic isomorphism, from the identification of N to L tensored up with analytic functions on the base. And so once again, this gives you some notions of the periods of V as a flat bundle, right? Which is just take a basis here, take a basis here, look at the matrix, and look at the coefficients. Okay. Now, given this local system, we pick the base point S, little s, remember? So we have an action of pi1 s little s on L. Particularly the fiber of L at little s. And let G be the identity component of the Zariski closure of the image. G is the algebraic monodromy group of our local system. Okay, so I think Sean asked about the transcendence degree, and you can get it quite directly from this. So here's a theorem we'll write down. I mean, it's already sort of, okay, it's basically known in the world of differential Galois theory. I'll write it here anyways. So here's how I want to say it. Actually, before I state it, let me define a couple more fields. So let me write K for the function field of S. And let me write KV for the function field of S adjoining the periods of V. So I'm starting to suppress the connection, even though, again, it's important with everything we do. Okay? So we have the field of rational functions and then some extension, some transcendental extension of given by periods. So the theorem is the following. So the first part is that in this generality, the transcendence degree of KV over KS is at least as big as the dimension of this G. And the second part is that if we're sort of in the good world, which is if V has regular singularities, if now much more connection, it's silly otherwise. Which is sort of the nicer case in many ways, though irregular ones are very interesting, as we've heard from several talks. And part of the reason I'm giving this talk is I'm curious about what happens in the irregular singularities case, which I don't think we have the right questions for. If V has regular singularities, then you get an equality. Okay? And I worked out an example, because I was curious when preparing this talk. I was like, oh, is this if and only if? Can you conclude from equality that it's regular singularities? And the answer is no. And so an example is on GM, you can consider some non-rational lambda, and you can look at the coordinate q for the function q to the lambda times e to the q, right?
Yeah.
So the connection here is really dz.
Q is the variable.
Q is the variable, yes. Q is the variable in GM. Dz plus lambda dq over q is the connection. So it's not regular singularities at infinity because of the e to the q and the dq over here. Then in this case, your g is the actual GM. You really do get a transcendence because you obviously do, and so you get equality, but you have irregular singularities. Yeah.
Couldn't you just say that you have always equality if you define G to be the differential Galois group and just
Yes, but I very much don't want to do that. The differential Galois group is like a more complicated. Oh, I see, but restate it and say they're equal in the whatever.
the regular case, the differential Galois group is this C closure.
Sure, yeah, you could say that. Yeah.
In this case, the differential, in this case, you have monodromy and exponential tools, and they generate the same thing. That's
Yes.
why it's.
You could, but some of the differential Galois group, in my understanding at least, I don't know how it plays with the periods at all. Whereas the regular
By
augmented
periods,
group.
you mean solutions of your connection.
Well, yeah, I mean the coefficients of the space chain, exactly.
Well, but it has a very. I mean, it acts by. There's a Stokes phenomenon that acts like monodromy, and there's exponential tools that.
Well, cool. So maybe you can, yeah. So I think you understand how it acts, but I'm still talking about it because, yeah, I don't know what to write down, but maybe that's the answer to some of these questions.
You want lambda to be irrational rather, right?
Sorry?
You want lambda to be irrational rather, or just so we don't trivial.
I think I want lambda to be irrational because.
You just wrote in Q.
Oh, sorry. Yes, irrational. No, that's sorry. Thank you. Yes. Because otherwise, I think you don't get GM. The fundamental group becomes smaller. Yeah. Mm-hmm. Okay. So. So let me give the. How many time? Yeah, okay. Yes. Let me give the proof. Let me give the proof in quotes. I'm not that good on time. Proof in quotes. So what's the idea here? Well, what you can do is you can consider homomorphisms. Look at the bundle, which is homomorphisms from V as a vector bundle to V sub S. Right? So this thing has a connection. There's a flat connection.
Really confused. What's V sub S?
So V sub S, so I have a base point. This is little s.
Little s.
Little s, yeah. Sorry, it wasn't little enough. Yeah, so from an arbitrary point of V, I map the fiber there to V sub little s. So as a bundle, it's just a bunch of copies of V dual. So then add the identity. So at little s, I have the identity map. So I get a leaf L inside this form V sub S. And this L is basically recording the periods for me as I go along with respect to this the appropriate chosen basis. Okay? So what I want to understand is the risky closure of L. Now, because of the way things are defined, this L is acted on. I'm going to action as I go around by the image of pi1 of S based at little s. And so if I'm going to be taking the risky closures, what I learn is that G acts on the Zariski closure of L. So it's a union of G torsors, the Zariski closure. And so the dimension is at least dimension G over the base. Okay, so that's part one. Part one is done here. So when would you want equality? Well, equality, sort of if and only if, essentially, G times L itself, which is a well-defined thing, it's a G torsor, is algebraic. Right, inside this guy. So you could prove this just with a regular Riemann-Hilbert correspondence, but because this sort of idea has been present in the conference and is present in the rest of the proofs, it's easiest to see with definability. So, oh no, but I guess the way I wrote it, you can't see with definability. Darn it. What to do? Okay, I'll give a definability proof anyways. I'll explain why it doesn't work with the generality in a second. So there's a result by Bakker, and Mulani, which says that if V has regular singularities, and this is the part we're missing, the eigenvalues, the residues around infinity have eigenvalues of norm 1. I'm just stating things now, I'm confusing myself.
The eigenvalues, local monitor, not the resident.
The eigenvalues, yes, thank you. That's right. That's right. Okay, which way am I? The eigenvalues of local monodromy, of the little loops around the boundary of monodromy at infinity, have norm 1. Then this equivalence actually descends to an equivalence of definable analytic spaces. For the R and X O-minimal structure. So instead of working in the analytic category, everything we've been doing can be done in the definable category. Okay, but then you finish in the usual way, because everything here is definable. This thing becomes definable. So therefore it's algebraic by definable channel. Okay, this is both overkill and doesn't actually prove the case where you don't have this. You can use regular Riemann-Hilbert correspondence to do that way, but I want to give a sense of sort of why this is true in nice circumstances.
You can prove it by standard Chow effect, right? Because if you just act by G, you get simply a univalued thing with regular growth. So
yeah, right. So what you need with regular growth, what do you mean by that?
Because you have regular singularity, you have at most polynomial growth, plus, I mean, you will have.
Yeah, so you can do that. If you need some argument to say you close nicely at the boundary, but yeah, you're right. And that is how essentially Riemann-Hilbert correspondence does it. Some argument like that. 100%. Okay, to generalize periods, so what I want to do is I want to now generalize the period map and give a theorem in that context. Okay, and so for that, I will need this notion of definability. So first, a definition. We have X, so we can look at the universal cover of X, and we can look at a map from X tilde Y, where Y is some algebraic variety. We'll call this map phi. And we'll say that this map phi is definable for any O-minimal structure, but as always, I really mean Rnx. If whenever you have a definable open U in X, and you lift U to X tilde, and then you compose to Y, this map here is definable. Okay, so essentially on fundamental domains, which you lift up to X tilde, you get a definable map. This is really an abuse. I mean, I think Gal would call this. What's your note? You had a note from your thought, anyways.
Near infinity, you want some kind of sector for V. And definable will imply it's not something which.
100%. That's why it won't rotate all the way around. Exactly. Exactly right.
So it sounds like the pi definability.
Sorry?
Just like this looks like the definition of pi algebraic. It's a pi definable.
A little, but it's a little bit, yeah, maybe a little bit. Mhm. Okay, and so now a generalized period map is the following data. So first of all, you have a Y with a G acting on Y with finite kernel. So essentially the stabilizer is going to be finite. And then you have a map from X tilde to Y, which is essentially surjective. In the appropriate sense, you have the fundamental group acting on X tilde, V acting on Y. We have a map here coming from our local system that we had over there, and we want this to be equivariant. So this map should be definable and row equivariant. Which is exactly what we get in the period map setting, right? We get a map to D check, which satisfies these properties. Now, given this kind of setup, given a generalized period map, Phi we can define C del phi as before. Right, pull back rational functions, apply derivations of them if you want. And the theorem that we really have is in this context, C del phi algebraic closure is equal to this cave. So you get all the periods from any kind of period map with no exceptions. This is always the case. Okay. So yeah, the idea is we don't end up actually using all that much about variations of Hart structure, period maps. We just use the existence of the G action. Now, the key for this part two of like you get equality in the original geometric setting, if and only if you have no unitary direct summon, that comes from this finite kernel assumption. Right? Because if you have like a Shimura variety with a compact factor, the group is acting, but a piece of the group is acting trivially. So that's not contributing anything, you aren't picking that up. In this case, by assuming G is finite kernel, you get this whole theorem. And yeah, and so okay, I'm not gonna write anything about the proof because I don't think I have enough time, but maybe I'll just say in words the idea of the proof, which is sort of twofold. It's sort of why do you I'm lazy, gotta bar both. Why do you land with these functions in here? So the derivations are fine because you have this is closing a derivation. But why do these functions land in here? What you end up getting is sort of a copy of the local system, giving you some function which sort of changes the right way under monodromy. And in principle, you can't say anything about this. Like if you had irregular singularities, there's lots of global functions that are irregular that like even the squared shows up. But because you're definable by the assumption there, you can somehow get that everything is algebraic, and so must come from the corresponding algebraization given by the Riemann-Hilbert correspondence And so you can sort of rebuild this vector bundle from this kind of data. And then why do you get everything? Well, that just comes back to this transcendence of G argument again. You can, through a similar method, get a G torsor from this construction. You can't do it just by the action on the Y, because like in the period domain case, your D check is too small. But because we're allowed derivations, you're allowed to look not just at Y, but at the jet spaces of Y. And having finite kernel eventually means you can find some torsor inside the jet space, which you pull back. Okay, maybe I'll stop here. Thank you so much for your attention.
Questions? So when you're doing the generalized period map, what is X here like S the base with the?
Sorry, yes. Yeah,
And so everything is just like pi 1 of S and then.
Yes. Everything is pi 1 of S.
And this nabla L is coming from the vector bundle that you've talked about. Okay.
Exactly right. Mm-hmm.
So I actually like so that theorem about differential Galois theory. So is that an application of the proof of the action for G principal bundles, the application, or is there any missing ingredients?
Sorry, what's your question? Like if you look at this theorem, how it
the proof idea you wrote. Is that just an application of the X channel for principal?
Oh, this is much simpler than that. No, the X annual stuff definitely has more ideas. Because Ben and I do something like this in our use of the X annual to prove this sort of undergrowthnic functional stuff. But to actually prove the X annual, you got to do more than look at the G torus. You got to look how it like intersects with stuff, right? So that's much more involved for sure. Okay. I mean, it's not that involved. It's a very clean proof, but more involved than this, definitely. Mm-hmm.
So, I mean, in the beginning, you were talking about periods defined over Q, and then you switch to the function.
Yes.
I wonder if I still want to take everything defined over Q bar, will this statement be true if I replace C by Q and some natural Q bar structure on the period?
So this statement probably can, because I don't know how to say.
I mean,
the original statement.
Because I thought that is what Bertan and Zudilin do, because they are motivated by kind of periods conjecture.
That's a good question. I think the answer is yes. I think basically you can prove.
It might just follow by linear algebra.
I think it follows because everything is transcendental, but everything's algebraic if you look at the power series expansions. And I think you can just show everything stays in Q bar. Does that make sense?
I thought that, once you know something is fuller, I mean.
No, sorry, everything, it follows immediately once you know that like it lies in the Q bar space to begin with. Yeah. So as long as you can get them in the same Q bar field, then yes, it's a formal consequence. And I think that's not hard. So yeah, I don't think that's a problem in the original setting. Mm-hmm.
How about the original? So those other ones.
Yeah.
You have nothing to say about those?
Well, not in this talk.
Yeah.
So a lot of that stuff was done in the functional case by Ayub and Nori and stuff, and then Ben and I proved the Andre Grothendieck generalization of that. But those conjectures sort of are much easier. Yeah, there's a lot to say about them, but yeah, not here.
Is there a regularity in this theorem or not? Do you need regular?
For what? For where?
In this theorem here.
Yeah.
Do you need regular singularities?
Yes. Just to get things to be defined, just to make the definable stuff make sense. You need regular with I'm getting so lost in my head. The local monodrome is of local system to have norm one.
Oh, I know one. Right.
Yes. But I think it's interesting. Like I was thinking about this because you can talk about generalized period maps without definability assumptions, and then I was wondering in the irregular case if you can sort of say what the right thing is in order to get back to this kind of thing. Of course, in the variation of Hodge structures case, everything is regular to begin with for free. But yeah, I don't know.
So you stated it as an if and only if, right? This like splitting off of unitary if and only if.
Yes.
So I see how because of this definability result one way, how do you prove the other way?
You're right. Like in the Hodge case specifically.
Yeah.
So in the pure case, it's easy because it's off. In the mixed case, you need some argument with like weight filtrations. That
I see. Okay.
Yeah, it's not hard, but it's not immediate. It's certain. Section 3 at the end of section 3 proves exactly this point.
Okay.
So we can talk about it after.
Sure.
Other questions? Okay. Thanks.